So in this video, we're going to take a look at some of the reasons behind the trends that we're going to see in atomic radius, ionization energy, electronegativity, and really looking at how Coulomb's law can explain this. So Coulomb's law was developed by scientist Charles Coulomb, and he observed the force of attraction between two oppositely charged objects. And he found that that force of attraction is directly proportional to the charges. And he found that that force of attraction is inversely proportional to the square of the distance. So as you discovered this for yourself, as you were playing with those magnets, you saw that as you held them closer, the force of attraction went up. So if the distance goes down, the force of attraction goes up. And you probably felt a really big difference in that force of attraction when you held them close. But then if you held them really far away, you didn't really feel that big of a difference when you change the distance, right? And the charge, you should have noticed that, hey, bigger the charge, the stronger the force of attraction. So you were able to kind of figure this out for yourself. And this could be put all together into a law that looks like this. And we're not actually ever going to plug into this and solve. But what is on your formula sheet is showing that this Coulombic force of attraction is, in this means proportional to the charge, directly proportional to the charge, and inversely proportional to the square of the distance. And they put R in your formula sheet. If you look up R, it says separation, but again, that is distance, the distance between those charged objects. And if just showing you, if you were actually to replace this with an equal sign, this K is a huge number, meaning that these forces of attraction are super, super, super strong. So you're never going to have to plug in, but you do need to know these relationships, that there's two things that are going to affect the force of attraction, and that's distance and charge. And that's what we're going to end up tying all of these periodic trends to, distance and charge, and how it affects the Coulombic force of attraction in your atom, which is the force of attraction between the positive, the nucleus, and the negative, the electrons, usually the valence electrons if we're looking at the outer edge of the atom. So if you want to fill that in strong, sorry. So the summary that you need to know, like I said, is that Coulombic force of attraction, and in your notes, you're going to see me write it as FC. When you're writing it, you might want to use the abbreviation they use on the formula sheet, which is F Coulombic. So F Coulombic stands for Coulombic force of attraction. It's just the force of attraction, but it's relating it to Coulomb's law. So by saying Coulombic, it's showing that you have knowledge of Coulomb's law, which is what they want in AP chemistry. So any of your explanations should always involve Coulombic force of attraction. If you don't know how to spell it, it's right here on your formula sheet. So the force of attraction between valence and electrons and nucleus go up if the charge of your nucleus increases. So the more protons you have in the nucleus, the greater the force of attraction between the nucleus and the electrons. And what does that mean? It means that everything's going to end up getting pulled in tighter, and you're going to start seeing a trend in atomic radius, and you're going to start seeing a trend in how easy it is to lose electrons or not, ionization energy, and you're going to see a trend in something called electronegativity, how much the nucleus attracts electrons. So it's all going to boil down to two things: charge, and when we look at charge, we're going to look at the charge of the nucleus, the number of protons, and distance. We're going to look at the distance between the nucleus and the valence electrons. The more that increases, the less force of attraction you're going to see. And this says this equation's not on the formula sheet. I apologize, I didn't update that. It is on your formula sheet. The full equation is not, but this relationship is. Okay, and please remember that like charges repel, opposite charges attract. So if you increase the charge of two oppositely charged things, force of attraction goes up. But if you increase the charge of two things that have like charges, they're going to repel each other more. Okay. So we're going to take a look at what charge and distance is going to translate to in the atom. So like I said, the charge is going to really relate to the number of protons, or the nuclear charge. However, how far you are from the nucleus is going to affect what charge you actually feel. And what I mean by that is we're going to use this term effective nuclear charge. And we are going to use this symbol ZEFF, because Z usually is the symbol for nuclear charge, and EFF stands for effective. So you can call this ZEF for short, but you know that that means effective nuclear charge. And what that is it's the charge from the protons, from the nucleus, that the electron actually feels. So it's the net charge. So what that means is if you have inner electrons, they are going to feel the charge of the nucleus more than outer electrons, because some of inner electrons will block the full nuclear charge from those outer electrons. So core electrons or inner electrons, which are closer to the nucleus, are going to feel more of this charge. So let's define a few words, and then let's look at an example. So shielding, we're going to use the term shielding for when inner electrons block the outer electrons from feeling the full charge, and the charge that they do feel, we're going to use this term effective nuclear charge, or ZEF. So let's take a look at a Bohr diagram for potassium. And here's the electron configuration. It goes all the way up to 4s1. And notice there's 2 electrons in the first shell. There's 2 plus 6, there's 8 in the second shell. There's 2 plus 6, there's 8 in the third shell. And there's 1 in the fourth shell. So here's a Bohr diagram. And for me, when you're doing a Bohr diagram, rather than drawing the dots, feel free to just write the number of electrons in each shell. So if I look at these inner electrons, the 1s2, which are right here, they are smack dab right up against that nucleus. They are feeling the full 19 protons, or the 19 plus charge of your nucleus. So they feel, if I was going to give them a number of what charge they feel 19 plus. They feel all those protons. They feel the full nuclear charge. So they are going to have the least shielding. There is nothing blocking or shielding them from the nucleus, and they are going to have the greatest effective nuclear charge, these electrons that are right up against the nucleus. Now if I keep going out, these electrons in my second shell, are they going to feel the full 19 plus? They're not going to feel 19 plus because they've got 2 electrons blocking the full charge. So instead of feeling 19 plus, if they're blocked by 2 electrons, what effective nuclear charge, what net charge do you think they feel from the nucleus? The answer would be 17 plus, because it's 19 minus 2 shielding electrons gives me 17 plus. And if I go further out, we're going to see that the effective nuclear charge starts to get smaller and smaller, because now again there are more shielding electrons. Not only is the first shell shielding, but now the second shell is shielding. So I have 2 in the first and 8 in the second, all blocking my 19 plus. So I've got 19 plus in the middle, but 10 electrons blocking it or shielding it. What is the net charge of this third shell, do you think, or the effective nuclear charge that they feel? 19 minus 10, what would that be? That would be 9 plus. And if I go even further out, this furthest shell, this 4s, this 4 shells, the furthest from the nucleus, there's only 1 electron in it for this particular atom. They are going to feel or experience the greatest shielding. They've got 1, 2, 3 energy levels or shells blocking it. So though there's 19 protons in the nucleus, there are 2 plus 8 plus another 8 electrons all blocking it. So if there's 2 plus 8 plus 8, which is 18 electrons blocking the 19 plus protons, what charge do you think this will experience? What would be the effective nuclear charge? It would be 19 minus 18 shielding electrons, which would only be a +1 charge that this feels. So what you're going to notice is the outer electrons feel the smallest effective nuclear charge due to the greatest amount of shielding. So these are great terms to use in a free response if you're trying to explain reasons behind the trends eventually that we will get to. Take a moment, pause the video, and I want you to draw Bohr diagrams for these 3 atoms, Na, Mg, Al, which are all in the same period, meaning the same row of the periodic table. Then check your work. Okay, so Na, Mg, Al. Na has 11 protons. I just picked the most common isotope based on the atomic mass, but doesn't really matter how many neutrons you put, but you should see that Na has 11 protons, Mg has 12, Al has 13. They all have 3 shells, but this is 3s1, so this would be 2, 8, and 1. This is 2, 8, 2, and this is 2, 8, 3. Notice I am adding an extra valence electron into the third shell as I go across the period, but notice they all have 3 shells. So what do they have in common and what's different? They have the same number of electron shells, all have 3 shells. And notice they each have 2 plus 8, 2 plus 8, 2 plus 8. They all have the same number of shielding electrons or inner electrons. So if I'm looking at this valence electron, let's talk about the effective nuclear charge each of these would have. This has 11 protons, but has 2 plus 8. It's got 10 electrons shielding it. So the effective nuclear charge that this one would feel would be a +1. This has 12 protons because we've added a proton now, but still only has 10 shielding electrons. So these outer electrons would feel a +2 because of the added proton in the nucleus. This one has 13 protons, but again, still only 10 shielding electrons. 13 minus 10, these outer electrons, which are all in the same shell and don't shield each other, would experience a +3. So the additional proton, but having the same number of shells, increases the effective nuclear charge. So what you're going to see is across a period, effective nuclear charge is going to always be your argument, almost always. Same number of shells, but increasing the protons pulls that outer shell in more and more and more. So even though I drew these all as the same size, in actuality, would they really be the same size? No. Which one would be pulled in the tightest? Al. 3 shells, but more protons in the nucleus, pulling them all in. These electrons, these outer electrons experience +3, where this is +2, +1. So effective nuclear charge increases across a period, but it has the same number of shells in each, shielding stays the same. Now take a moment, pause the video, draw these Bohr diagrams for these 3 atoms, which are all in group 2, which is the vertical column. Here's Be, here's Mg, here's Ca. Notice that they don't have the same number of shells. Every time I go down the group, I've added one more shell. So Be has 2 shells. Mg has 1, 2, 3 shells. Ca has 1, 2, 3, 4 shells. And the number of shells should relate to what row or period it's in. So Ca is in the 4th period. That's why it has 4 shells. So each has an additional electron shell. Oh, what factor is changing now that relates to Coulombic force of attraction? Not necessarily charge, but distance. Every time you increase the number of shells, you're increasing the distance. And how does that affect the Coulombic force of attraction? That makes it go down. So we can also use the word shielding. There's more shielding in Ca than there is Be. Now you might be like, hey, look, the number of protons is going up too. Isn't charge going up, and wouldn't charge be an argument? Well, let's actually calculate the effective nuclear charge on the valence electrons. So this has 4 protons, 2 shielding, so this would experience a +2. This has 12 protons now, but now it has 10 shielding electrons because we've increased the shielding. 12 minus 10, oh, that's also +2 on the outer. Okay, here's 20 protons, but I've got 2 plus 8 plus 8, I got 18 shielding electrons, so still those valence electrons only feel +2. So what you'll notice is the effective nuclear charge actually stays the same down a group. So it's not changing. So you never want to use an effective nuclear charge argument down a group. It's all the same. Yes, you've increased the protons, but you've increased the shells and the number of shielding electrons, and those two things cancel out. So shielding or distance is going to be your argument down a group. Effective nuclear charge is going to be your argument across a period, and that's what's going to help us explain these different trends soon. So shielding, as we said, increases down a group because you are adding an electron shell. And the more shells you have, the more shielding electrons you have that shield the valence electrons from the nucleus. Effective nuclear charge increases across a period. You have the same amount of core electrons, the same number of shielding electrons, but you're adding a proton, which pulls all the electrons in tighter. So notice that shielding is going to increase down a group. So down a group, we're going to use a distance argument. You've got more shells or more blocking electrons. And across a period, we're going to use a charge argument. And again, those two factors are the two factors that tie into Coulombic force of attraction. Distance, which we're using for a group. Charge, which we're using for across a period. How I calculated effective nuclear charge was I took the number of protons and I subtracted the shielding electrons. And we're assuming that core electrons are the things that are shielding, and things in the same energy level do not shield each other. So if you have 3 valence electrons, those 3 are not shielding each other. It's the shells before those that are shielding it. Okay, so take a moment, try this example. Which would have a higher effective nuclear charge, Li or Be? Calculate it. And then do the same for this one, Li or Na? Calculate it. Pause the video, check your answers. So for Li or Be, here's Li, 2 shells, 3 protons. So 3 protons minus the 2 in the first shell would give me a +1 effective nuclear charge. And Be still has 2 shells, still 2 shielding electrons, but I've added 1 to the nucleus. So that gives me a +2 effective nuclear charge. So Be would have the higher effective nuclear charge. Which one would be smaller? Even though I drew them with 2 shells, Be has more protons, so it would get pulled in tighter. And then for this one, Li or Na, here's Li again. I just drew it before. You don't have to draw the Bohr diagrams in doing this, but I'm just showing you to visualize it. Here's Na. Notice Na has 3 shells. But even though it has 3 shells, it has more inner electrons, so it actually ends up having the same effective nuclear charge as Li. Things in the same group are going to have the same effective nuclear charge. Now, on the AP exam, I've never actually seen them have you calculate effective nuclear charge, and you never have to do it. You can just say something has a greater effective nuclear charge than something else without actually calculating it. So if I know, for instance, Be versus Li, Be is further down the group, it's further down the period, so it has more protons, I could just say Be has a higher effective nuclear charge than Li due to more protons. I don't actually have to calculate these numbers, but it's helpful to have as a tool in your toolbox. Okay, so the takeaway here that I really want you to know is that across a period, same number of shells, here's Li, Be, boron, carbon, all have 2 shells because they're in the second period, but I'm adding a proton. This added proton pulls everything in tighter. It increases the Coulombic force of attraction. So across a period, we are going to be using a Zeph argument, an effective nuclear charge argument. Across the period, more protons, more effective nuclear charge. Don't use the trend as an argument. Don't just say, oh, this is further down the period, so it has higher effective nuclear charge. Give me the why. More protons, more effective nuclear charge. Down a group, we're not using a charge argument. Effective nuclear charge is actually the same as we saw. We are using a distance argument. So you could say more shells or more shielding, but relating that to distance and Coulombic force of attraction. If this is a free response question, you are using this term, Coulombic force of attraction. If you want to abbreviate it, feel free to abbreviate it the way they do it on the formula sheet. But you want to say across a period, this has a higher effective nuclear charge, so it has a greater Coulombic force of attraction between protons and electrons. Or down a group, we're saying more shells means more distance and a lower Coulombic force of attraction due to bigger distances between the nucleus and the valence electrons. So again, mentioning that Coulombic force of attraction, it is a hot spot. These are going to be all the reasons behind a trend. If you're explaining a trend across a period, you're going to use effective nuclear charge. If you're explaining a trend down a group, we're going to use distance. And we will continue this another class.